again. This short animation supplements the information in the pressure ulcer lecture about McClemont's cone. I thought it might be useful to work through the principles behind that concept. You'll probably recognise this image from the PowerPoint presentation. I'm not very artistic at all, so please bear with me when I give you my own take on the pressure gradient that McClemont describes as a cone of pressure. The first thing we probably have to acknowledge are the differences between the various types of tissue which are breached during pressure ulcer development. Okay then, first layer is the epidermis, stratified squamous epithelial tissue, not really metabolically active. Moving on, the dermis. We've all sorts of activity going on here. For example, synthesis of collagen and elastin, so much more active in metabolic terms. Then the adipose layer. It's a major repository for energy and for maintaining body temperature, so stuff going on here all the time, pretty active. The final muscle layer, which is the most metabolically active of all of the four tissue types, constantly oxidizing carbohydrate or fatty acids to provide the fuel to contract and relax the muscle fibres. Right, a little recap. The differences between the tissue layers are the extent to which they are or are not metabolically active, and perhaps, a bit obviously, is there is differences in the amounts of these tissues relative to each other. Now we've got that out of the way, go back down to the epidermis and exert some external pressure here over a bony prominence. Immediately that external pressure transfers through the epidermis. The problem we have though is how that pressure reacts when it hits the interface between each subsequent type of tissue. The interfaces are here, here, and here. At each interface, pressure increases in severity, so each of the four layers of tissue is subject to a different pressure and an increasing pressure, with the muscle layer bearing the greatest pressure of all. This means that the least amount of pressure is experienced at the epidermis, coincidentally the least metabolically active of the layers, and the maximum amount of pressure is experienced in the muscle layer, which is the most metabolically active. And that gives us this picture of a gradient of pressure increasing in severity from the epidermis to the muscle. In practical terms, this means that there is the potential for tissue damage to go deeper and wider than we can tell from examining the external surface of the skin. Finally, do you recall I made a comment earlier about the size of each of our four layers relative to each other? I want to show you that same diagram with four layers, but you'll see this time we've got notably less adipose and muscle tissue. Now the concept of a pressure gradient hasn't changed, doesn't change. What does change though is there is an increase in the severity of pressure as it travels through every one of those layers of tissue, compared with the previous diagram which represented, if you will, normal skin. Now that means that in a situation where we have less tissue between the external pressure and the bony prominence, the pressure gradient is greater and therefore the risk of pressure damage is correspondingly greater. And that has clinical significance for us. Thanks for watching this. I hope it helped you a bit with the concept of McClemont's cone.